In the previous video, we saw that models help us to isolate the effect of the independent variable upon the dependent variable. And they do so by making the assumption of ceteris paribus. That means all other things remaining equal, although in real life they almost never do. For example, suppose the price of eggs were to go up by, say, $1 a dozen. We might naturally conclude from a little model that we build in our head that the quantity of eggs demanded, that is, the amount that will be purchased, will go down. It makes perfect intuitive sense. However, it could be wrong if, let us say, that on the very day that the price of eggs went up, I hit the lottery and won $100 million. I might buy eggs for the entire neighborhood. In such a case, when the price of eggs went up, the quantity of eggs demanded would go up. So, should we say then that when the price of eggs goes up, the quantity of eggs demanded will go down, except if the consumer hits the lottery? Well, no, because I can think of a number of other situations that would also affect the outcome of our model. It could also be that on the very day in which the price of eggs goes up, the doctor tells me that I am not consuming enough eggs and that I must triple my intake of eggs in order to cure whatever disease I may have. In that case, I would consume more eggs despite the fact that the price of eggs went up. Should we say then that when the price of eggs goes up, the quantity of eggs demanded would go down, except when the consumer hits the lottery or is prescribed more eggs by the doctor? Well, of course not, because we can go on and on and on and on, thinking up situations that might contradict the results of our basic model. So what we need is this. We need to eliminate all of these exceptional situations and assume that they do not exist. Nobody wins the lottery. Nobody is prescribed more eggs by the doctor. There's no change in your likes or dislikes for eggs. None of that stuff happens. Your income, your wealth, your health, your tastes and preferences, all of that stuff remains the same, although in real life, it never does. How do we hold all of these things constant? We do so by saying when the price of eggs goes up, the quantity of eggs demanded will go down, ceteris paribus. That's Latin for everything equal. So by ignoring the impact of these extraneous variables, we get rid of the noise that obfuscates and clouds and muddies the relationship between the relevant variables. So models are about expressing the relationship between variables. There are three ways in which we can express a relationship between variables. They are the schedule, the graph, and the equation. A schedule is simply a table that lists selected values for the independent variable, and then right next to them, the corresponding values for the dependent variable. Consider the model that we constructed in the previous video where we examined the relationship between study time and grade point average. Let's call study time S and grade point average G. And let's construct a table. First, let's select a set of values for the independent variable. It doesn't matter what they are, but let's use the ones that are most convenient. There is a very convenient set of values for the independent variable study time. Now, right next to it, we're going to list the corresponding values for the dependent variable grade point average. Let's also construct a schedule for another relationship that we had considered in our previous video, and that is the relationship between miles run and body weight. Let's select some values for the independent variable miles run. We'll call that M. And then right next to it, we will list the corresponding values for the dependent variable body weight, W. Notice that by reading the schedules, we can easily see that the relationship between study time and grade point average is direct, and the relationship between miles run and body weight is inverse. So let's assess the usefulness of schedules. Schedules are easy to write and easy to read, but they can only show a limited number of observations. For example, in the case of rainfall and crop growth, we only showed 7 observation points before we got tired of writing it down. Additionally, schedules become exponentially more complicated as we add more variables. Trying to show the relationship between rainfall, temperature, fertilizer, and their effect on crop growth by use of a schedule becomes real complicated real fast. So that brings us to graphs. First, graphs are easy to construct and easy to read once you get the hang of it. But unlike schedules, a graph can show a virtually unlimited number of observations. However, like the schedule, graphs become very, very difficult or even impossible to construct for multivariate relationships. Now, the basis of a graph is 2 intersecting axes. As you can see, these intersecting axes divide this space into 4 areas or quadrants. The vertical axis is the y-axis, and that's the axis for the dependent variable. The horizontal axis is called the x-axis, and that is the axis for the independent variable. On each axis, we mark off incremental values. On the y-axis, the values above the intersection are positive, the values below the intersection are negative. On the x-axis, the values to the right of the intersection are positive, those to the left of the intersection are negative. So now let's express the relationship shown here by a schedule on a graph. The first xy pair shows that when x is 0, y is 2. As it turns out, this xy pair can be shown by a single point on the graph. Now, what makes this particular point unique to this particular xy pair? Is it the color of the point, the shape of the point, the size of the point? No, none of that. It is the address of the point, and the address can be found at the intersection of the coordinates x equals 0 and y equals 2, which is right here. Keep in mind now that the x-axis is the one on which we measure the independent variable, and the y-axis is the one on which we measure the dependent variable. Now, the next pair in the schedule shows that when x is 1, y is 3. We can express this pair as a point on the graph at the intersection of the 2 coordinates. And we can do that for all of the xy pairs. But as mentioned earlier, one of the drawbacks of the schedule is that only a limited number of observations is practical. For example, this schedule does not show what y will be when x is 2.5. But this schedule is simple enough that we can interpolate that y would be 4.5. And that point would appear right here. Although the x equal 4.75, y equals 6.75 pair doesn't show up on our original schedule, it shows up on the graph right here. We could do the same thing for a lot of other xy pairs that don't appear on the schedule. And if we do it enough, these points on the graph start to get blurred and indistinguishable. And these blur of points actually starts to look like a line. In fact, we could draw it as though it were a line, but keep in mind that it only appears to be a line. It is, in fact, a bunch of tightly squinched together points, each of which represents an xy pair. Now, we can call this line y equals f of x, meaning that y is a function of x. That f means is some function of. Now, we'll see this more clearly when we talk about equations in a few minutes, but it's basically saying that the value of y is dependent upon the value of x. By examining the schedule, you can see that the relationship between x and y is direct, and that direct relationship shows up on the graph as a positively sloped function or line, one that slopes upward to the right. So let's do another. You'll notice that when there are no negative values, as in the case we're about to do, we only need to draw the first quadrant of the graph where all values are positive. So let's mark off increments on the axes, and now let's show the schedule. Here's the first xy pair, 0 and 8. Here's the second, 1 and 7. And here's the rest of them. Rather than showing a whole bunch more, let's just cut to the chase and show the line that represents the relationship. By examining the schedule closely, you can see that the relationship between x and y is inverse. That is, when x goes one way, y goes the other way. And that negative relationship shows up on this graph as a negatively sloped function, one that slopes downward to the right. Just to show the limitations of the graph, let's add another independent variable to the mix. Let's call it z, thus making this a multivariate relationship. Now, as it turns out, this relationship between x and y only exists when the value of z is 1. The problem is that when the value of z is 2, a whole new different relationship exists between x and y. Now, on the graph, z will need its own axis. So now we have a three-dimensional graph. When we only had two variables, x and y, we only needed a graph with 2 dimensions, height for the y-axis and length for the x-axis. But now that we've added z, we need a third dimension, depth. Rather than trying to plot this relationship on the graph, let me just show what it would look like in the most generic way. Let's get rid of the increments here and just sketch out what the function would look like in this case. As you can see, this function would be two-dimensional rather than a single-dimensional line, and would look like a triangular pane of glass leaning up against the y-axis. Now, if x and y were here, then y would be here. it would be too tedious, too time-consuming, and would shred the last fiber of our nerves trying to actually plot this on the graph. Now, let's add another independent variable. Call it A. The schedule would become unbelievably complex, and it would be impossible to express this by means of a graph. A graph would need a fourth dimension, and humans can only visualize 3 dimensions. So this relationship can't be shown by a graph, and although it can be shown by a schedule, it would be unimaginably complex. So what do? You're right, the equation. Equations are very convenient ways of expressing relationships between variables. And once you start working with them a little bit, they become very intuitive very quickly, and they're much, much better at expressing relationships than our graphs or schedules. They can show bivariate relationships, they can show multivariate relationships, linear relationships, or even curvilinear relationships. This is what a curvilinear relationship looks like. But this isn't a math class, so let's just show how an equation works with a bivariate linear relationship. Here is the general form of a bivariate linear relationship, which of course is the most simple. As you can see, there are 2 Greek letters in this equation. The first one, alpha, which of course is the first letter of the Greek alphabet. It looks like a Roman letter A a little bit, but you can draw it like a fish swimming to the left. Of course, you wouldn't draw the dorsal fin or the eye or the mouth, and certainly wouldn't close off the tail. Just a simple loop is good enough. The next letter, beta, looks like a Roman letter B, except that it's got a long tail. I found that it's easier to write if you start with the tail. Look at that. You can make a really cool looking beta this way. But don't let the Greek letters intimidate you. This is the very same equation that you learned in high school algebra. Y is equal to mx plus b. The alpha is the b, and the beta is the m. This is the way they write it in social sciences because it's actually easy to decipher than the y equal mx plus b equation. The Roman letters, x and y, are the variables. X, of course, is the independent variable, y is the dependent variable. The 2 Greek letters, alpha and beta, they represent the parameters. Parameters are constants, and these constants contain the information about the relationship between x and y. The alpha parameter tells us what the dependent variable will be when the independent variable is 0. For example, how high would crops grow if rainfall were 0? That's what the alpha parameter would tell us. What would be your body weight if you ran 0 miles? What would your grade point average be if you didn't study at all? That's what alpha tells us. It tells us what the dependent variable will be when the independent variable is 0. Now the beta parameter is the action parameter. The beta parameter tells us what the dependent variable will do. There's that action word, do. What the dependent variable will do when the independent variable goes up by 1. Let's consider a schedule that we used a little bit earlier. There it is. It's easy to see what the alpha parameter is. When x is 0, y is 2. Alpha, therefore, is 2. Now, can you figure out what beta is? Notice that when x goes up by 1, from 0 to 1, y also goes up by 1, from 2 to 3. Again, when x goes up by 1, y goes up by 1. And we can see that this is the case for the entire relationship. When x goes up by 1, y goes up by 1. Therefore, beta is equal to, you guessed it, 1. By replacing the symbols for the parameters with their actual values, we are transforming our equation from the general form into one that is more applicable to this specific situation. As you know, when the coefficient of a variable is 1, as it is in this case, in the case of x, you don't actually have to write the 1. So then we could simply write the equation as y is equal to 2 plus x. Now let's check our work. Let's select a value for the independent variable x at random, say 5. Now let's plug in 5 into x and solve for y. And as you can see, y is equal to 2 plus 5 equals 7. And as you can see in the schedule, when x is 5, y is indeed 7. Let's do it again, just to make sure. This time, let's plug 2 into x. Our equation then tells us that y is equal to 2 plus 2, which is 4. And let's check that against our schedule, and we can see that sure enough, when x is 2, y is 4. Let's consider another schedule. Here's our general form. Now, take a moment to derive the alpha and beta parameters here. Pause the video if you want. As you can see, when x is 0, y is 100, and therefore the alpha parameter is 100. As you can also see that when x goes up by 1, y goes down by 5, and therefore beta is -5. Let's see what that looks like when we plug these values into the parameters. Now we can make this a lot easier to look at if we get rid of those parentheses. So let's test our equation. Let's plug some random variable into x, say 6. And now let's crank through the equation, and we see that y then is 70. And we can see that when x is 6, y is 70 is consistent with our schedule. Now let's do one a little bit harder. This one is harder because the value of alpha is not obvious as it has been in our previous examples. What is obvious is that beta is +10. But in order to derive the alpha now, in this case, we're going to have to make an assumption. As you can see, this schedule represents a linear relationship, one whose function on a graph is a straight line. And we can see this because the beta coefficient is constant throughout. And that constant beta is what makes it linear. Now, let's assume that the relationship remains linear from 1 to 0. Probably not too heroic a leap, but we need to state it anyway. That would mean then that when x falls by 1, y falls by 10. Then, when x falls by 1 from 1 to 0, y will fall by 10 from 50 to 40. That would make our alpha parameter 40. And our equation therefore becomes y is equal to 40 plus 10x. Now, let's see if our equation is right. Let's plug in some number into x, say 6. Y is equal to 40 plus 60, which is 100, and that is indeed consistent with our schedule. Now, there's one more item on the agenda that we need to explore. We have thoroughly explored the relationship between a bivariate linear equation and a schedule, but now let's explore the relationship between equations and graphs. Let's use an example we used a few minutes ago. As you can see, the schedule illustrates an inverse relationship between x and y. And when we draw this on a graph, it would produce a straight, negatively sloped line. But now let's take a look at the equation. Okay, that was pretty easy. On the graph, the value of alpha is the point where the function intersects the y-axis. The value of beta, on the other hand, is the slope of the line. Now, let's talk about slope for a few seconds. The slope of a function is pretty much its slant, and it is computed as the rise of the line divided by the run. Here on the graph is the function's rise and its run. Here's the function. Now let's plug in some values and compute the slope of this function. Upon close inspection of the schedule, you can see that for every increment that x increases, y falls by one increment. So the slope of this function is -1 over 1, which of course is -1. On the graph, when x rises from 3 to 4, y falls from 5 to 4. Alpha gives us our starting point. Beta gives us the slope of the function, which is a reflection of the intensity of the relationship. As you can see here, the function is positively sloped but very flat, indicating that x has a direct, as opposed to inverse, a direct but mild effect on y. In this case, beta would be a relatively low positive number. Now in this case, on the other hand, beta would be a relatively high negative number. So now, after having seen this and the previous video, the one on models, we see that models are about ignoring noise so that we can identify the basic relationship that exists between the relevant variables. In this video, we saw how we can express those relationships between variables by means of schedules, graphs, and equations. Now, let's apply this knowledge to a very important model in economics, the supply and demand model. Although not perfect, this model goes a long way in explaining why the price of something is what it is and what will cause it to go up or down.